all different store. I think it's really
Great, so everyone, so let's get started. So welcome back. So today we're going to talk about word vector embeddings, which are both like a really interesting data set, kind of like an exemplar sort of data set where kind of there was this large revolution in like how we're able to process and understand language. And kind of the first, I think the first important step that really unlocked this was these word embeddings. So we'll talk about these not only as an interesting representation of data, we will so we'll talk about how these laid the foundation for like a lot of these so chatbots like ChatGPT. So we'll also talk about them in the context of self-supervised learning. So in this class, I kind of told you we were not going to do full supervised learning. We're not going to do classification and regression, but we are going to talk about so self-supervised learning, a lot of data minus unsupervised learning. So I'll explain why self-supervised learning is kind of, I think, fairly new perspective on this that has really bridged the gap between the two. There are these other approaches like active learning and other things that are or semi-supervised learning that have tried to bridge the gap, but really the self-supervised learning idea has kind of had the most impact. At least from my perspective. I'd say active learning is pretty important as well. Okay, and so these word vector embeddings and this approach of self-supervised learning has kind of not just kind of had impact on how we model language, but has impact on how we represent and model and kind of without explicit supervision, a large amount of other data as well. So we will kind of, I will explain this kind of in the context of word embeddings, but I'll kind of try and give pointers to how this has been so very kind of is kind of had influence in a lot of these other areas. Okay. I'd like to look at this schedule. You should be looking at the homework for locality-sensitive hashing. There have been a lot of good questions out about that. There are a few pieces in that homework we did not get to cover yet that I'd hoped to cover in an earlier lecture. Explicitly, one of them will be about generating. I asked you to generate a uniform sample from the space of high dimensional unit vectors. This will kind of fit in, and we'll do some wrap up with locality sensitive hashing in the lecture on Wednesday. But I want to start with this random generation of these these unit vectors because that'll show up on your homework. And the reason we kind of I've inserted these two lectures in between the two on the kind of locality-sensitive hashing and also the context of similarity search is I really want to kind of instill the importance of the representation of data as kind of these high-dimensional vectors. And so locality-sensitive hashing we saw kind of in most in depth with this min-hashing framework, but it's probably most famous for its use with respect to Euclidean vectors in between for Euclidean distance or the using cosine distance. So I kind of this previous lecture and the lectures today is really motivate why this is such a crucial representation of data. Okay, so before we get started, there was this question on your homework where I asked you to generate a set of IID kind of U1, U2 up to U kind of T of these vectors that are uniform from S d minus 1. Remember, S d minus 1 is going to be the space of all these vectors in RD, such that X, the norm of X is going to be exactly equal to 1. Okay, so the space of unit vectors. Okay, and so if we have the origin here, then the space of all of the unit vectors, right? This will be S kind of d minus 1 if the whole space is RD. Okay, so I only want these vectors. So one example, U would be, I can think of it as a vector here. You could also think of U as being kind of this one, and so U of 1, U of 2, up to U of D, where these are the D coordinates of this vector. So I can represent again as this D-dimensional array, or I can think of it as this vector in the space. So then you can think of it as a vector from the origin, and then it always lies on this ball, this perfect ball of radius 1. Okay, so I want to generate vectors from this space. This will be a really important operation to do, and you'll have to do it on your homework. And so it turns out it's not hard. It turns out it's not hard to do, but it's not something you'd probably kind of try and come up with on your own. All right, if you were to try and generate data on this sphere just in 2 dimensions, so on the 1-dimensional circle, how would you generate data uniformly from the circle? Any thoughts on how to do that? Yeah?
Generate and then solve.
Oh, okay. So step 1. Okay, I'm going to generate, let's say, a value between -1 and 1. Okay, so that would be some value, the X value here, right? And then I need to figure out what should the Y value be. And so in fact, I typically have an operation where I can generate this real value uniform between 0 and 1. Okay, so this is often built in, and I can do this by generating, I'm going to say this is equal to 0 plus bit 1, bit 2, bit 3, where I'm writing out the kind of the bits, the kind of in binary. So bits times kind of a log of some n. I generate enough bits that's effectively random. Each of these is 0 or 1 at random. Okay, so if it's all ones, then in binary, that's basically gives me a value of 1. It's all zeros, it's 0. And then this is the leading order bit. If the first one is 0, then it's under 0.5 and so on. So I can generate a uniform random value from random bits, which you can imagine the computer can generate stuff based on noise and in the processor speed or some other process. So I can generate one value between 0 and 1. And I might want to generate, okay, let's start with one value between 0 and 1, and then I scale it by 2, and I subtract 1 from it. Now it's between -1 and 1, right? Okay, so I can start with this. But I've already reached a problem. Then I want to generate the second value, but the first value already has the wrong distribution. Okay, there are, in fact, there's more. If I look at the density, even here, the density should be higher here on the edges because there's more arc length of the blue curve on those edges than there is in the middle, right? So there's kind of more arc length here. And so the first bit already has the wrong distribution. So this is a good starting point. We have some operation we can do. But this already is not going to quite be uniform on that blue circle there. Okay, what's another idea? So good. All right, so generate an angle, okay, which is in kind of which is uniform between 0 and 2 pi, right? And I can do this by 0, 1 and then multiply by 2 pi, right? I've got 2 pi stored in a kind of hard-coded someplace, right? And so I can generate this, and this will kind of start at the top and walk around the circle, so some distance, and I can, and then use some trig functions to get into 0, 1. Right, so this works actually really well in 2 dimensions onto the circle. Could I do this in 3 dimensions? Now I want to generate points on a sphere. Maybe it's a little bit trickier. In fact, it's a lot trickier, right? And it's a lot trickier. This works for d equals 2. It's hard for d, I would say, greater than 3. You could probably do it in d equals 3, and the trig gets more complicated, but it's going to be tricky to get, again, the distribution right. Right, choosing the first angle, there are ways people have studied how to do this, but it gets really messy after d equals 3. Okay, so this isn't going to quite work for high dimensions either. Remember, I want to do this in like 300 dimensions. Yep.
You generate random points in virtual space and normalize them to.
Okay, good. Good. So I want to generate points in d-dimensional space, right? And so the first idea probably is you think I want to generate points in the box, maybe by 0, 1, 0, 1, and then I'm going to normalize them. If I generate points in the box, I could say, well, so V1 through V2 up to VD, which each are in uniform 0, 1. To the power d, I do this d times independently, and then so normalize. Okay, so then I can do this normalization operation. Okay, now if this were to generate points in this region here, only inside of the ball, then this would work. Okay, but if I generate points inside the box, what's happening is that in some direction here, going straight up, I don't have as many points as I do in this direction here. If I point towards the corner, I get more chances to be on the blue curve. So it's not an perfect distribution. And it turns out in high dimensions, this ratio gets really, really bad. And almost all the points are going to be in these corner spaces. The corners get really, really big in high dimensions. Most of the mass is out there. Okay? But this idea of generating points in high dimension and then normalizing is the right approach. But we need to generate different from the uniform distribution over the box. Okay? Okay. Anyone else know what the answer is before I tell you? Okay, so what we're going to do is you're going to generate kind of points V1 through V2 up to, actually I'll call them G1 through GD. These are going to be IID from a normal distribution. Okay, this is normal. Okay, and then I'm going to get a vector G, which is G1 up to G. Turn G divided by the norm of G, right? So I'm going to generate these normal random variables or generate sample from a normal distribution in each dimension independently. Okay, and then I'm going to get a vector here, and then I'm going to normalize it. So two normals here, but this is L2 normalization, so that the length of it is exactly 1. Right, and so this is the algorithm we're going to do. What I have not told you how to do yet is this step. Okay, but we want to generate from this normal distribution. Now this, okay, if you remember the normal distribution, this is like this, 0 here. The standard deviation is 1, and there's this normal distribution. It's going to be, let's see, the right. Okay, just so I get the normal 0, 1 is going to be a G of X, where X is 1 over 2 pi, so 1 over square root 2 pi e to the negative X squared divided by 2. Yeah, by 2. Okay, so this is the normal distribution, and I need to somehow sample from this. Okay, now this seems just as hard as a bunch of the other things we said, but there's this cool trick called the box. So the Box-Mueller transform, okay, which takes I take two uniform random variables between 0 and 1, and I'm going to transform these into two Gaussian random variables. Okay, in this weird way, they're going to be independent Gaussian random variables. G1 is going to be equal to, I need to look this up, U1, the square root of the natural log of U1 times the cosine of 2 pi U2, and G2 is going to be -2 of natural log of U1, square root of this times sine of 2 pi U2. Okay, so now these two are going to be independent random variables from a normal distribution. So I can turn two uniform into two things from normal. That tells me I need to do this d over 2 times. I get these d normal values. The Gaussian, which is the kind of normal distribution in multidimensional normal distribution, which is what that G vector is from, is the only kind of, is not the only, but is kind of the easiest distribution to sample from that is rotationally invariant. Okay, so I can generate the coordinates independently and it's rotationally invariant. So if I rotate it, it doesn't change. That means that if I normalize the vectors, unlike on the square, because it's the same distribution along any kind of subspace, any one-dimensional space, that if I normalize it, I get exactly unit vectors on the sphere. Okay. So this is how you do this in the homework, and it's in section 5.31 in the notes as well. So if you don't get it from up here. All right, so this is kind of a really cool and kind of, I think, important trick that we'll use a bit later. So we can generate high-dimensional uniform. This is a random direction. You can think of this as a random direction in high-dimensional space, and this is how you do it. Okay. Cool? Yeah.
What's wrong with just generating twice and then averaging to get like the central limit? Wouldn't that also be normal distribution?
Oh, so I can generate a bunch of these vectors from the box. So I do this where I generate a vector from this box here, and then I'm going to repeat it m times for some large number m and take the average over these. And the argument is this will in the limit converge to the normal distribution or something like it from using the central limit theorem. In every one-dimensional subspace, it will converge to a normal distribution, but depending on the direction you choose, it'll be it's going to be a different normal distribution that will. So along this axis pointing towards the corner, it'll be a normal distribution, but it will be wider than the normal distribution pointing along the axes, right? So they'll all be normal in the limit, and but they will not be uniformly long in each direction. Yeah, so that's an interesting idea. Also, I would have to repeat this whole thing where I generated d of these uniform random variables a large number of times and average them and hope that this worked. Whereas in this one, I only have to generate d uniform random values, pass them through this process, and I get out d Gaussian random variables, which I can then normalize just once. Okay, so interesting idea, but it's not quite going to give you what you want. So cool. Okay, great. This will be a trick that we will use later on in the semester. Okay, so I want to talk about word embeddings. Okay. So how many people have worked with word embeddings before? Few of you, and how many people have played with them, have heard of them, at least in some context? Okay, about the same number of people okay, so a handful of you have done them. Okay, and what the concept here is I want to somehow run machine learning on like natural language. And so the old school way of doing this was you would start out with this, with like a sentence, the quick brown fox jumped over the lazy dog. Okay, uses every single letter of the alphabet. That's one sentence. So what they would do is they would try and first take a sentence like this and identify like this is the verb. Okay, so so then there would be kind of the kind of the object of, or I guess this is the subject of the sentence, right? This is the fox is the thing that's doing the acting on it. They would try and understand this. This is the subject. These are quick brown fox or adjectives. I think they're modifying fox. Okay, and then over it jumped over is part of the verb jump, right? And analyze the sentence this way. We would look at the sentence, try and identify the parts of speech, and then trying to say, okay, break down the sentence in this way. Okay, and so it was kind of most of natural language processing up to about maybe 12 years ago. Almost all of it started at this point, right? You start with the sentence, you try and decompose it, learn its parts of speech, and then use that to analyze what was going on. This was the first step. And so this was hard to do, and it was, once I had this, it was hard to use these parts as well, right? It was also hard to make sense of this. So this kind of newer approach said, I want to kind of map each word. Let's say the word fox, right? I want to map this into a vector in some high-dimensional space, right? So I'm in, this is RD. We're going to think of D is equal to, say, like 300. Okay, and so now fox, so there's a vector labeled by fox. It's going to be some vector in the space. Okay, so in a 300-dimensional space, that means I'm going to turn the word fox into an array of size 300. It's going to have a bunch of numbers in it, and somehow that's going to capture the context of what fox means. Okay, and then the idea is that, well, if I have a similar word, let's say the wolf, right? Maybe the wolf vector is somehow close to the fox vector, that these are close. Okay, the wolf and fox are maybe similar types of animals, right? And they're first of all, they're both nouns, they're both animals, and there's maybe similar types of animals. And so they should be embedded near each other, again, in a very high-dimensional space. Okay, and the big premise behind this, so the premise of how this should work, what words should be close to each other, how do I determine that? And it was not, there's this work called WordNet that tries to categorize all words into kind of different categories. Okay, it's a noun, it's an object, it's an animal, it's a mammal, and that's a type of mammal. And so how these words are similar, it's not using that. Okay, it's trying to use some simpler premise, is that words are similar if they appear in similar context. Okay, this is known as the distributional hypothesis. Okay, and so this was made by, I guess, by Firth or Harris, kind of before people were doing this. This was kind of a linguistic way of thinking. Which words are similar to each other? Well, if they appear in language in similar contexts, then they are similar words. Okay, and that's the context here by which we want to embed fox and wolf, the vector representations close to each other. Somehow, if they appear in similar contexts, then their vector representation should be similar. And by similar, I mean probably the cosine similarity is large. Okay, which usually maps to the Euclidean distance is also small. Okay, so this is kind of the premise we're working with, the distributional hypothesis. I somehow want to turn this into kind of from the distributional hypothesis into that the embeddings are going to be similar under cosine or kind of Euclidean distances. Okay. All right. So this is kind of the underlying main idea, and let me talk about kind of the progression of how the field managed to do this. Okay, and there are kind of 3 generations of this. And I'm going to start out with kind of the first generation that did not really kind of work much in practice, but the first gen, I'll call these PPMI vectors. And this was more used as a concept of what it should be than was actually made a big difference in practice, because these were not very practical to do. And these are going to, so the idea is that every, so if I have my sentence, quick brown fox jumped over a lazy dog. Okay, and I want to look at the word fox. Okay, then I'm going to look at its context, which will be the words nearby it. Okay, and a common kind of, remember this C continuous bag of words thing I mentioned earlier in the semester, that one way of building this context is to look at all the instances of the word fox. So I have a big corpus of text. Think of a big novel like War and Peace, or look at all of Wikipedia, or eventually they trained on like all of the internet, like a web crawl over the internet. And so I want to look at every instance of the word fox. And then for that, where it appears in the text, I want to look at the nearby words. Okay, and there are kind of 2 ways of doing this. What is, and this would be called the context window. And there are 2 ways, either kind of n words on each side, or it's going to be, let's say k words on each side, or k words before the word in question. Okay, so either I would look at both sides, and usually this was kind of the initial model of doing it, and then there was also when I just look at the words before. Okay, and sometimes you don't want to know what comes afterwards, and this is useful in generating language. Okay, so I want to look at the words in before, and I want to aggregate the kind of bag of words, which is going to be the number of instances of say jumped, so J equals jumped, in any context window of, say, fox. Okay? Oh. Okay, so any context window of fox, right? So if fox is going to be a word I, then this is going to lead to a value Bij. Okay, so for each word, so this I is the kind of word in question, right? For example, fox, and then the J is going to be possible word in its, so possible word in context, so jumped. Okay, and I want to compute these statistics across all the context windows. Okay, so if I have a data structure that's storing a big vector, right? I can think of storing, I can store a big vector that is going to be an M by M kind of matrix of counts, right? So Bij J is going to be this value Bij here. So I'm going to create, I'd have to store this huge matrix here, M by M matrix. For each word that appears, I have to count for every other possible word how many times this other word appears. Okay, this is a lot to keep track of. Roughly how big is M? Right? How big is this value M that we'd need to keep track of? About how many words in the English language are kind of, do you think these models would pay attention to? Yeah. It's like 100,000 is a good guess. So there are about 100,000 words that these models would pay attention to. Most language everyday language you can get by with like 10,000 words or less. But for this, let's say 100,000 words. If you count weird common misspellings and things like emojis, you can maybe get to 300,000. Okay, so it's 100,000 words. So that'd be 100,000 by 100,000 matrix. So this is not very practical, but this is kind of a conceptual first step. Okay, so I want to keep track of these counts nearby. Now, this aren't quite the vector representation. So I could think of is this frequency context vector Bi, which is going to be equal to Bi1, Bi2 up to Bim, right? Again, this would be a vector in Rm. Is this a good representation? Okay, is this a good representation by itself? It's probably not, right? There are going to be certain words like the word the or of or and. Together, those words take up maybe 8% of all words you ever use. Okay, these kind of stop words. The first 10 words probably take up about 10 to 15% of all the words. And these are going to kind of dominate these vectors. They're not going to tell you that much useful information about the context. So what they do is they want to convert this into something that looks like a log likelihood. Okay, so I'm going to do a couple of steps. I'm going to do Pij is going to be Bij divided by n, where n is the number of words in the corpus. Corpus is like all of Wikipedia. Okay, so in the corpus, so this is kind of a probability of seeing something like this pair of words. Okay, not exactly that, but up to some factor, dividing by the context window size. Okay, and then I want to look at like the log likelihood, and they often convert it into something that looks like, so I'm going to look at the log of I want to do one other thing first. I want to do Pi is going to be Ni divided by N, where Ni is going to be the number of times word I occurs. Okay, the word I occurs. And then I'm going to get a pairwise pairwise probabilistic mutual information which looks at Pij divided by probability of I times the probability of J. So now I'm normalizing by, if I have the word the as one of the pairs, well, I'm dividing by the probability of the word the. Okay, so if the occurs a lot, I expect it to occur a lot with I if J is the word the. Okay, if it's a rare word, then I'm dividing by a small number and this becomes more important. We often look at the log of this probability. Okay, and then you often, values which are negative, we often don't like. So we'll take the max of this and 0. So the log of something, if for some reason PI and PJ is going to be kind of for everything where, let's see, if PI and PJ are more likely individual than PIJ, okay? So these are both common things, but they don't occur very commonly together. Then this will be less than 1, and the log of it will be negative. And at that point, I say, well, this is kind of not a very interesting correlation, so that's going to make it sparse. I'm going to round this to 0. Okay? And so this will be, I'm going to call this Vij. This will be kind of some value Vij, which is going to be a useful representation of Vi. Yeah.
So what exactly is Vij representing in context? Likelihood of the probabilities, or what do we get?
Yeah, so it's this is called the positive pairwise mutual information. Okay, so that's positive because I rounded everything up to 0. Pairwise because I'm looking at the pair of them, and this is called the log of this is the mutual information shared between, meaning how likely are they to occur together. Okay, and so this was kind of a common model of co-occurrences that there's some papers that talk about this because it was easy to work with and calculate. The question is, did they start with this and said this was the right thing, or did they kind of back derive this as what they were working with once they had an algorithm? I'm not totally sure. I've heard the latter side of that, but I'm not totally sure. I don't know the authors so personally. Okay, but this positive pairwise mutual information kind of became something that you would want to represent as giving you information of if the word I co-occurred a lot with the word J, with the word 2 here, then this value would be large. And that would say there's some interesting context between the word I and the word 2 that would show up in this vector representation of word I, right? So this is RM, and this was thought to be a useful vector representation of the word I. Okay, so if 2 words, now the idea is if 2 words have a similar Euclidean distance between their positive pairwise mutual information vectors was small, or the dot product with them was large, then they would probably have similar context to each other, and those words should be treated, they should be embedded in a similar sense, right? And this would give them similar embedding if their context was similar to each other. Okay, so this is a way of representing this. So now we can represent them in a way where the cosine or Euclidean distance gave a useful representation of was a useful proxy for how similar are the words. Yeah.
I guess using your example, if I were fox, J were dog, you would expect Vij to be relatively large.
Well, Vi and J, not necessarily. Would fox and dog appear in the same sentence near each other? So it wouldn't be fox and dog they wouldn't necessarily co-occur with each other, but they would say the dog jumped, the fox jumped. Those are both reasonable phrases, so that their vectors would be similar. They would both have often would common with both of them because they're a noun. So we'd say the dog, the fox, and jump is something it would do. So jumped would be a common word to see after it, right? So the vector representation is capturing the kind of the average over all the context windows, right? So it's averaging over the whole corpus, all of Wikipedia, all of the internet. Every time the word fox occurred or the word dog occurred, look at the context windows look at all the frequencies of those words, compare them against how commonly those words occur in practice across all the documents, and give a sense of how similar their contexts are, not the words themselves, right? Okay, so this is the first big idea, that we could represent them based on their context. This is what was probably the, there were a number of probably competing ideas, but this was kind of one of the cleanest ones. Okay, and this was one that was directly adapted into the second generation. So that's why I described this way of representing. Okay, so I want to think of, this is 100,000 dimensional vectors. So it's a real pain to work with. The good thing is, oftentimes I'm going to round to 0, but that might be, say, half of them are going to maybe round to 0. So that might not be that useful. It's still fairly dense, and it's super high dimension. So just keeping this whole matrix of all the words around was not very, very, very practical. Okay, so the second generation, the second generation says we wanted vectors vi that was in RD, where D equals, say, 300 became kind of a common, about the sweet spot for these things. So now it's still 100,000 words, but only 300 dimensions, which was much more attainable. You could do 100 dimensions, but turned out you would gain a lot of functionality going up to about 300, and you probably did a little bit better in higher dimensions beyond that, but it started to become more painful to work with. Okay, so we want vectors in 300 dimensional space that captured something like but we want them to work like the PPMI vectors. Okay, I would call this this is the PPMI vector. Okay, so I wanted to work like that, but in 300 dimensional space. Okay, so even approaches, I mean, one approach that I was kind of trying to, I tried out, my research group tried out around this time, which didn't work so well, is to one, get the PPMI vectors, and then do dimensionality reduction, which is a family of techniques we'll talk about a little bit later on in the semester. So do dimensionality reduction. This is in RM, to go from RM to RD. This did not work as well as these other approaches. Okay, so a better idea was to learn this kind of mapping to our RD using this approach I was talking about called self-supervised learning. Okay, and this led to these representations called word2vec and so glove, and glove directly was trying to learn something that preserved the similarities described by the PPMI vectors. Word2vec was optimizing something slightly different. Okay, but thematically they're very similar. They came out around 2013-14, and this kind of really doing these, because they're only in 300 dimensions, they were usable, and this became kind of the first step everyone was using in natural language processing. Within a year or two afterwards, most of a bunch of long-standing benchmarks saw like 1 or 2 decades worth of improvement over the next like 1 or 2 years. But you first represent all the words in using these fixed word representations and then ran some machine learning on top of it. Yeah. When did those, this was, okay, so the way I know them is because that's how they justified what they did in the glove paper. Okay, and they claimed, I mean, there's some references that before them, they weren't really commonly used, right? Because they were so big. They wasn't really a practical. They were earlier. I think they were discussed. So probably in like the noughts, right? The 2000s, before 2010, there were these thing called, what was the name of this? So topic modeling. So topic modeling was where you took a bunch of text documents and you embedded in each of them in some space, kind of like with the min-hash vectors, and then did something like dimensionality reduction or clustering on top of that and claimed you found topics of these. The groupings of these were kind of like topics of this. And they were based on ideas like positive pairwise mutual information. But there were other models as well, like perplexity is something that was similar, but it looked something like this. So in the 2000s, the aughts, I guess, is there noughts or aughts? I don't know. That's when this sort of thing was popular, but they didn't directly model individual words like this. This was not practical. It was too big. Okay, so this idea, they did this for documents and something like, it's very similar to, so TF-IDF is a very similar idea, which is a way of representing the importance of words within documents and context. And that was very popular dating back to the 1980s. So, okay, so these ideas had been around a long time. And this happened in 2000, around kind of 2013, and things changed, like immediately had a huge impact, right? Like everyone shifted gears within a year, and my friend was not quite running down the hallway, kind of excited, but kind of like people were very excited about this. Okay, Word2Vec was out of Google, and Glove was out of C. Washington and Allen and Suva. Okay, okay. And there are other versions that came afterwards. Okay, well, let me talk about let me not get to what came next yet. Let me talk about a little bit how these worked. And they use this idea called self-supervised. So learning, okay? And so if we start with supervised learning, okay, in supervised learning, the input is going to be xy, which is this set of these xi, yi pairs, right, where x is from some space, often, this is often Rd, and this is each xi, and each yi is often some given label. And in kind of two-class classification, for instance, it's -1 + 1 in regression, right? So this is classification, this is regression, and these are the labels, and the labels were often, yeah.
What's that in the subscript for the input xi whatever?
This is some space. There's some kind of space of objects. X.
The inputs. It says input x.
Xi, y. Usually what you think of a vector y, y1, y2 up to yn. And each of these is 0, 1. And this x is going to be a matrix, and x equals x1, x2, up to xn, and I'll often think of this as a vector, as a matrix, and n by d matrix. So this is in -1 is a n-dimensional, right? This is n-dimensional vector. And it's what's important is that you're given data, which is your so this set x1 through xn, this is going to kind of be the independent variables, and I want to somehow use x to make a prediction on y. So I want to use this to make prediction on the yi, right? So each xi from xi to yi. So there should be some function that I'm going to learn, and I want to kind of, what machine learning does is it learns this function f, where the output of it should be close to the value yi. This is what supervised machine learning does. Okay, and yep.
So y's are actual values, or are they just
Y's are the labeled values I'm given as part of the input. Okay, so well, I haven't, I'm going to describe this for words in a second. In words, we're going to use self-supervised stuff, but I want to remind you of classic supervised learning first. Okay, supervised learning, you're given a bunch of data and you're given labels. The labels are often assumed to be given by an expert or some scientific observation. So think of, you have patients and the x's, each xi is one patient, and then there's a doctor who says they have cancer or they don't have cancer. That's yi. Or I'm making some scientific observation in the field. I'm going to say, I'm going to measure this flower, right? I found a flower in the field. I'm going to measure the length of its petals. That is yi, is the length of the petals of some observation I have. Okay, and this is a painstaking process. Okay, generating labels. I remember 15 years ago, everyone was like, yeah, we have machine learning, we can scale stuff up, but how can we get more labels? The labels, we don't have enough labels, right? Around 15, 20 years ago, kind of the big data revolution, computers got really good at generating a bunch of data, storing the data, and kind of computing on the data, okay? But we didn't have a lot of labels. The labels were still hard to get. And it's still the case. You know, like there are things like the CAPTCHA when you're checking if you're an AI or a human. These don't really work as well anymore. But the whole point of the CAPTCHA, you had to identify a fire hydrant or something, right? That was you giving a label to a machine learning algorithm. They developed these things, CAPTCHAs, partially to get labels because it was so hard to get these labels. Okay, a lot of images in ImageNet as well, people labeled their photos they uploaded to Flickr or someplace with a little caption. That caption was kind of the label of what was in there, but it's not, it's imperfect, right? If the gold standard was you had a doctor said this person definitely has cancer from the scan or they don't, or an actual measurement by a scientist someplace. The labels are hard to get, okay? So the problem is the labels hard to get, okay? So this is supervised learning. So the question is, how do we get to the supervised learning for text, right? Well, we get to what's called self-supervised learning, okay? And self-supervised learning is kind of a way of trying to train the data on itself, okay? So, and I'm not, the first example I'm going to give, again, is not going to be text. Learning, so I basically train on data xi to predict itself or part of itself. Okay, so the kind of the most common early way of doing this was an example would be so like would be an autoencoder, and this was common with like images. So I have an image which I'm going to represent as its pixels, right? So most So I'm going to think of an image as a series of pixels, and each black and white, they each have a value in each of the pixels, or color channels, and there are 3 times as many values as pixels. Okay, and that's thousands, if not hundreds of thousands of pixels. And so, and what an autoencoder does is it somehow takes this as input and it maps it down to a lower dimensional space. We call the encoder. Okay, and I'm going to get a lower dimensional space. So this would maybe be RK, a k-dimensional space. And then I'm going to get a decoder. Okay, and the decoder was trying to represent, so if this was xi, right? So this would be xi tilde, and the goal is that xi minus xi tilde, the squared norm is small, right? So the sum of the squared differences between xi and xi tilde, I want this to be small. So I want to learn the encoder and the decoder, and they have some parameters, you know, theta and theta 1 and theta 2 in these functions. Okay, traditionally it's a neural network, but it could just be like a low rank approximation. Okay, the early ones, the earliest idea basically here was like was eigenfaces. There are a bunch of data sets of people's faces, and you can do an eigen decomposition of this, and you got a low rank approximation. We'll talk about this later in the semester if you haven't seen this before. But the more common ones now is they'll build some sort of fancy neural network with a bunch of kind of convolutional neural network or transformer models inside of these. And then you want to recover the pixels at the end and measure the L2 distance here. Okay, so it can learn itself. There's no training data here, but I can learn these functions to encode the faces in a small dimensional representation. Okay, and if k is equal to the number of pixels, I can just have this be the identity function. But typically k is much smaller, and by forcing it to be a smaller representation, then it has to do something clever. Okay, in order to match the output on the input, I have to do something clever in between. Okay, so this was an early example of self-supervised learning. Okay. Okay, so they were supposed to, these work pretty well. They're pretty cool. Hopefully a lot of you have heard of these before. They tend not to be perfect, right? To recover the image really crisply, like these generative models nowadays, this is not quite what they use, because when you go to a lower dimensional space, I have to lose something. And so the objects on the other side tend to be a little bit blurry. Okay, but this was a way that I could learn something from itself with no labels. And I kind of learned a way of a k-dimensional space on the space of all the faces, for instance. So it's kind of a neat trick here. Okay, how do I do this with text? Text did not use this, and this kind of made things blurry. Okay, so these are often so blurry. There's some tricks you can do to improve it and stuff, but this is the community has kind of moved on from these for the most part. Okay. Okay. For text, what's become common is what I would generally call a masked model. Okay, we'll go back to our sentence. Quick brown fox jumped over the lazy dog. Okay, and so what does the masked model do? Well, it would say, let's look at the context of the word fox, but not give it the word fox. So I'm just going to take this guy. Let me just rewrite it. Quick brown blank jumped over the. Okay, so I'm just given this context and I'm given an empty spot here. And so I want to predict this word which is missing. Okay, so how do I predict this word that's missing? Okay, so this is what I'm learning here is kind of the structure of the English language. Right? I can learn the co-occurrence in this context. What is the most likely word there? Okay, and so I'd use it. Well, so how would I do this? Think of this context. This is this context here. And eventually I'm going to somehow map this to a K where say K equals a 300-dimensional space. Okay, so I want to take this context and somehow with some sort of like, initially these were like long-term, short-term LSTM models or something, or kind of these other fancy things they invented in neural networks that use as much anymore, and they mapped them into this 300-dimensional space, different layers of the neural network. And the hope is that in this space, now I'm going to get a vector vi, and then I'm going to have a data set, let's call this vi tilde, of v1, v2 up to vm, which is going to be in 300. And I'm going to guess that vi tilde is going to be approximately the nearest neighbor of vi tilde. Okay, so maybe I say that the true word I here, right, is going to be the nearest neighbor. So I'm going to find the nearest neighbor in this high-dimensional space. I can do this with locality circle patching, or by just checking all of these, each of the words kind of against each other. And I'm going to guess that the true word is the one that's the nearest neighbor in this high-dimensional space under cosine distance or Euclidean distance. Okay. And so if it's not the right word, well, then I say I want to move this vector closer to the right word and further away from the word that was similar. And that sends some like gradients back through here, and I do some back propagation, and I learn the parameters here. Okay. And so I've done this. I've learned the context without building this 100,000-dimensional vector. I can directly learn this 300-dimensional vector using kind of this self-supervised learning. I'm just scanning over text, and every time I shift the context window, and instead of predicting fox, I predict the word jumped, right, with a slightly different context. And then I predict the word over, slightly different context. So I slide the context window, and I do a prediction. So I scan text, and I update my gradients. Okay, and so this was how we learned these embeddings. These were now learned embeddings without any explicit labels other than being told, this is example of the English language. So the supervision is, okay, here's text. I believe this is English language. I want to train a model that respects the context characteristics of all this text, and that will give me embeddings similar to the pairwise, positive pairwise mutual information vectors. It should capture the similar context of the words. Similar words have similar context. And this, based on the distributional hypothesis, gives me a good notion of similarity between words. Okay. Okay, and so this is basically what the glove model did. The RoBERTa model, I think, unless I'm getting them mixed up a little bit, looked only at the context window with, if I have a context window, came only before the word fox, okay? So what this allowed me to do is do next word prediction, okay, where I'm starting to write text, right? And I write text up to a point, and then I use this to predict, well, what is the next word I should pick? Well, I look at the context window of what I've written so far, and then I guess, okay, here's what a good next word could be. And I can do this like probabilistically as well. I don't always have to use the closest word. I can find the closest 5 or 10 words and pick one of them, maybe depending on how close they are to each other. Okay, and this was the basis for how generative language chatbots work. Okay, now there's another kind of layer after this, but this is basically how they work. They look at the context window before, I want to predict the next word, and I use this model to predict what the next word is. Okay, and if you train this on all of Wikipedia, it will output stuff that looks kind of like English, but it doesn't make any sense. Okay, it doesn't have a lot of meaning to it, but it will look a lot like something that could be English language. Like the grammar looks reasonably good, but what it's saying isn't necessarily very, very, very meaningful. Okay. Okay. And this idea of this self-supervision, this applies to, I want to spend 10 more minutes going to kind of contextualize embeddings. But this applies to other data. Okay, so this is how most of the graph embeddings work. So if you've heard of graph neural networks, you have a graph of data where nodes and edges, and you want to kind of embed the nodes in a high dimensional space. You compute a bunch of random walks in the graph, and then you predict which is going to be the next vector, and you use that to do the embedding. Okay, if you have you can do this for some images embedding. There are other ways now, but you can kind of take a big image and you can mask out a piece, and you don't let the kind of neural network see what this piece is, and you try and predict what should be in that piece. Okay, you can do stuff like so spatial data. Where you take spatial data and you mask out the surrounding and you guess what should be there, say geolocated tweets, or where should be a fire department there or not. You can look at transaction data in like in fintech. Well, a bunch of transactions. What is the next transaction that this customer is going to have? Okay, so a lot of these techniques, there are a lot of embeddings out there, like genomic data. They have embeddings like this, where what is the next kind of sequence in the DNA, RNA going to be, right? Where you have these sequences of things, and if you can use this to mask a piece and predict what is next, and if you have enough data, this will give you some embedding, and that will allow you to predict all sorts of things. Okay, let's talk about the third generation. Okay, the third generation now is, I would say, is probably a little bit more specific to text. Okay, this is what is kind of by this, I mean things like, so there were kind of two things that came out. So ELMo and BERT, which turned into RoBERTa. Is this capitalized? Okay, so ELMo was out of the University of Washington and OpenAI, and BERT was out of Google. This came out in like 2019, is that right? And kind of ELMo came out, and before it was, and they put it on the web right before they submitted it to a conference that was going to be out like 4 or 5 months afterwards later. And before it was even presented at the context conference, it was already obsolete by like RoBERTa. So I'll explain what there were two innovations that came literally right on the heels of each other. Okay, and initially people were so stoked by ELMo, it made a big improvement over Glove and WordTabac. And within a few months, kind of it was dominated by BERT, and then RoBERTa came like a year later. Okay, and there were two main ideas here. The first one is contextual embeddings. Okay, and the problem this was solving was that these words, so homonyms, okay, these are words like, so like the word apple. Like apple is a fruit, it's also a company, right? Okay, so if I do an embedding of the word apple, it has two very different meanings depending on whether it's referring to the fruit or as the company. And those should not be embedded in the same place in RD, right? So it's got two different meanings for the same word, but the language embeddings did not know how to embed these into two separate locations. And there are a number of words like this, and these cause some issues. So what the idea in ELMo was to do a embed, was to learn, a function f theta, which took the context plus the word and map this into RD. Okay, so I want to somehow learn the function. And so the key was that every time there are some parameters in this function, every time I saw a word, a context in word, I wanted to try and embed it differently. So the embedding of it depended not only on the word itself, but also on the context that appeared with it. Okay, so it was not a single thing, but I still wanted to predict the word, and I could use the context in order to predict it. So if I said, I went to the Apple store today and got a new computer, be different than I bought an apple from the grocery and ate it, right? Those are different contexts with the word apple, and I would predict different locations based on them. I would predict differently which version of that would appear. Okay, and so this embedding the context meant that there was no longer a single representation of a word anymore. So it was not as nice and geometric, but I could every time. But the way these were used is I was reading over text, and every time I saw a word, I would embed it into a space, and I would take this and then run some other machine learning on top of that. Well, I would do this the same way, but now I use the context to get a different embedding every time. So it fits within the paradigm, even though I no longer got these high-dimensional vectors, which is kind of something we will like to think about the rest of the class. But for NLP, this became kind of, it worked much better. And for instance, if you use this to generate language, it worked much better because it paid attention to the context more and what word would come next. Okay, the second idea, okay, were these transformer architecture. So with this idea called attention, okay, and I'm not going to explain exactly how this works. If you take a class by like Anna Marasovich, she'll try and explain to you. It's okay, but we're not going to explain how this works. But the idea is these previous techniques, including so ELMo, could only work in kind of a limited size context. I had to have a function, and basically it had a fairly limited, maybe a fixed size of how much I could fit into this model. But with the transformer model, I could have much larger context. Okay, much larger context, and it's because it doesn't weight all the context. It does not weight all the words in the context as equal. Okay, it picked out the attention, takes in a long sequence of tokens, and it picks out the most influential things in predicting the last word. Okay, the attention selected this attention, this selected the most influential words in the inside the context. Okay, so I could have a much bigger context now, so I could look back several sentences in order to predict what should come next. And this allowed us to do this in kind of a scalable way. Okay, and I don't have to learn the whole. It's not just the word distribution of the words that came before, but it's kind of what they meant in some way. The transformer helps select the most influential words, and that would help like predict what the next word was. And when you plug these two things together and you train on huge amounts of text, all of a sudden we really understood how to generate stuff that looked like the English language and kind of made sense with a larger context, right? And this, like RoBERTa, is basically still the state of the art, more or less. There's a new version out recently that tunes a few things, and this is kind of the base of what's in OpenAI's like ChatGPT. There's a bunch of training and other stuff they do on top of that, and now much more reinforcement learning to make it work better. But this is the base representation of how they do that. Okay. All right, I'll probably summarize this and make a few more points in the next lecture, but we'll stop here.